Um, so on that note, what do you guys want to work with today? Any topic that you feel you want to do? Circle theorems. Are you guys okay with circle theorems?
Yes, sir. Can we do
Yes, sir.
circles?
Circle theorems. Do you want to do
Yes,
both?
sir.
Okay, sir.
Go over a few basics. I had prepared a PowerPoint presentation, and I just put together something. Just let me check and see if I have that still. It might take me a few seconds to get that going, so just bear with me. Just a few seconds. Okay, let me share the screen. Okay, these are a few of the circle theorems. Just take you through this. Can you see this, guys?
Yes, sir.
Yes, sir.
You can see the full screen version, right? I've put the full screen version on.
Yes, sir.
Yes, sir.
So, circle theorems. Okay, just a quick look at what a tangent is. A tangent to a circle is a line which touches the circle at exactly one point. For every point on the circle, there's a unique tangent passing through it. So for a particular point, there can only be one tangent. Like for point A, you cannot have any other tangent that touches the circle at point A except for this particular one. Of course, since a circle can have infinite number of points on its circumference, you can have an infinite number of tangents. Right? But at one particular point, there's just one tangent. And again, a tangent is a line that touches a curve or a circle at only one point. Okay. Secant. You may not come across this too often now, but a secant to a circle is a line which has 2 points in common with a circle. So it's a line that goes almost through a circle. Okay, so it touches the circumference at 2 points. Um, and and a secant that's inside of a circle also forms a chord, right? So AB forms a chord. All right, so far, okay, right? This is just basics.
Yes, sir.
Okay. And then we come to the first theorem. That's the tangent perpendicular to the tangent. A tangent is perpendicular to the radius at that point of contact. Okay. So your tangent here is xy, and it touches the circle at P. And from P, if you draw a radius, then that radius is perpendicular to the tangent. So you can see that from the figure, and I'll just sort of reconstruct something on the side. So this is a circle, and let's say I have a tangent that touches the circle at about one point here. And from that point, if I draw a line to the center of the circle, which is the radius, all right? The green line is the radius. That tangent and the radius make an angle of 90 degrees is what this is trying to say. All right. So it can be with any other tangent also, any tangent at any point. And if that were to touch the center, would always be 90 degrees. All right. So tangent and the radius at the point of contact are perpendicular. Is that fine? So this is one of the easier ones. Okay. Also, before we go on to any other theorems, one thing I'd like to mention, and this is a very basic fact, but it doesn't strike many students, and this is the fact that all tangents in a circle are of equal length. Okay. Many times that obvious fact does not strike us because we're looking for other things. So if you had this triangle, what would be the relationship between these two angles, guys?
They would be equal
They would be
because
equal.
it's an isosceles triangle.
Well done, Naren. Excellent. And Anaria, did you know that these two angles
Yes,
would
sir.
be equal?
Yes, sir.
And you know the reason as well, right?
Yes, sir.
Because
Because
these
both
two
is,
are radii,
yes.
and the base angle, and they form an isosceles triangle. The base angles of an isosceles triangle are equal.
Yes, sir.
So we can move on from here. This theorem is okay for you guys?
Yes, sir.
Let me know, okay?
Yes, sir.
So two tangents are of equal length when a tangent is drawn from an external point to a circle. Okay. So from the circle, there's an external point, some random point somewhere, okay, and that point is P. So from that random point, you can only draw two tangents. Only draw two tangents, or maximum of two tangents. You can draw one, of course, but you can draw a maximum of two tangents. And both of those tangents will be equal in length. Okay, so that fact is pretty important. Those two are equal in length. Okay. And let's say I were to draw a line. Let's say I were to draw this the center of the circle. Let's say I were to draw a pair of lines. Okay, this and this. All right. And these are the radii, right? These two are the radius.
Yes, sir.
And this would be 90 degrees angle. You agree with that? Because the tangent and the radius are
Forms the
perpendicular.
90
We
degree.
just learned it in the previous theorem. Okay with that, guys and
Yes,
Ria?
sir.
Yes, sir.
And if I were to draw a line through the middle from the center of the circle to that external point here, you might come across this scenario quite a few
Very,
times.
very often, sir.
Numericals, lots of numericals based on this. Just remember a few facts, okay, with this scenario. Um, these, let's say this point is O, okay? Let's say this point is O. And the triangles OTP, not one time password, OTP and OT1P and OT1P are congruent. I'm claiming that they are congruent, but are they really congruent? Should we check?
Yes, sir. SAS.
Yeah. If you look, these two angles are equal, right? This angle and this angle in those triangles.
Yes, sir. And then two radii and one common line in
So
between.
angle OTP is equal to angle OT1P, right? So OT1P, because both are 90 degrees. Then, yeah, you're right. The radii are equal, correct? So OT1, the line OT1 is equal to the line OT because they are radii. And OP is equal to OP itself, right? That's because it's reflexive or common. I don't know what you guys say. Do you call it reflexive or common? Whatever the reason is, okay? So this is equal to itself. So this is a right angle triangle. So this is a right angle, this is a side, and this is the hypotenuse. You can even say that they are true by RHS. Okay, heard of RHS? Congruency? Naren, Analia?
Yes, sir.
Familiar to you? RHS. So
Yes, sir.
basically that means when two triangles are congruent in such a way that their right angles are equal, their hypotenuses are
Hypotenuse
equal,
and
and one
one
side,
side.
yeah, any one of the other sides is equal. So that's called RHS. Okay. All right. So in now, when these two triangles are congruent, the reason I brought the congruency into the picture, it means all the corresponding sides and angles of, I mean, all the corresponding sides and angles are equal, which means that this angle will be equal to this angle, and this angle will be equal to this angle. Okay, because they'll give you some unknown angle here. They'll say this is 25 degrees. And then they'll ask you to find some other angle. Now, because we know this fact, this is 25, so this is 25, and this is a right angle, right? So this would be 65 degrees, and then this would be 65 as well. Something like that. Okay, don't go literally by the angles. One looks smaller than the other. This is the theory that is there behind it. And let's just say, are you following this, right, Naren and Anaria, so far?
Yes, sir.
Yes, sir. Yeah.
Let's just say I draw some line through this. Right? Let's just say I draw some line through this, some orange colored line through this, say at this particular point. So in this scenario, what would happen? What would I be able to, as of now, just given this little piece of information, as of now, could I be brave enough and know what these two angles would be?
Yes.
Yeah.
Oh,
Can I tell what these angles are? Okay.
oh,
Narena,
yes, sir. Yes, sir. Because
but one sec,
two
hold
radius.
on.
Yes, sir.
Anaria, have you got this? Would you be able to calculate these two angles?
No, sir. I have no idea how you got that.
Okay. I sort of brought this point up earlier, and I think Naren has figured it out. Naren,
Yes, sir.
the magic word is radius here.
Yes, sir.
Okay. And Anaria, did you follow why
So
the magic word is radius?
you said it's equal, like all the radiuses.
Correct. I was just saying in the previous theorem, right? When we were doing the previous theorem, I said this is such an easy fact, but so many children miss out on this because we are thinking of a billion things, right? Except what's right in front of us. So this line and this line are radii, which makes this triangle isosceles. And if you knew the top angle, the vertical angle of the isosceles, you'd easily know what these two are, right? So if that's 25. These are whatever's remaining from the 180. Divide that into two parts. So 155 divided by 2, each of those angles. Got it?
25.
Yeah.
Got it, sir.
That fact appears a lot more times than you think. Just the knowledge of that fact that the radii are equal and they make an isosceles triangle, that one single fact appears a lot of times. Okay. Okay. So because of this sort of structure, this sort of thing, these are the things you need to consider. Okay, in this familiar looking diagram, uh, first know that those two triangles are congruent, which means all their lines and angles are equal. Also, the radius and the tangent, fact that the tangent and radius at that point of contact are perpendicular. Okay, also know that the radii, if they make a triangle, two radii involved in a triangle, that triangle will be uh, isosceles. Okay. Is that okay? Is that fine?
Yes, sir.
Yes, sir.
Can move forward, right? So just reiterating, um, the two tangents drawn from an external point are equal. Okay? And just previous two theorems, the tangent on one theorem we had, right? A tangent is perpendicular to the radius at that point of contact. So okay with both of those theorems, right? So far.
Yes, sir.
Yep, sir.
One more, and that's the angle in a semicircle is a right angle. Okay, so this is a diameter. That this baseline is a diameter because that's the center. Just draw the diameter here. Um, and from this diameter, if you draw any triangle such a way that the opposite vertex touches a circumference, then that angle is 90. Just again drawing the circle, drawing a diameter from here. And no matter where you draw it, even you draw this little tiny line over here, and if I were to join these two, that angle would still be 90 degrees. You're probably wondering why. Is that thought occurring to you? Like, why would this be
Yes, sir.
90? And why would this also be 90? Say this also would be 90. The same thing. It looks unlikely that both of these angles are the same. Correct? How can it possibly be that both of these angles are the same? Right? I mean, if you were to take out a if you were to take out a if you were to draw a proper circle and draw the diameter and draw these two angles, you will find that they're equal. But there's a geometry way of proving it, and I think we need to go one theorem ahead. Have you guys heard of this theorem which says that from a particular arc, from an arc, okay, I'm going to highlight that arc, this arc. From this arc, I've drawn an angle onto the circumference, right? You know what that means, Anaria and Naren?
No, sir.
Oh,
Okay.
yes, sir. I know this one, sir.
So, Anaria, in that circle, the yellow line is the arc, okay? An arc is a piece of a circumference.
Oh, that I know, sir.
You know what an arc is. And from this arc, I've drawn two lines that make an angle onto the circumference, okay?
Okay.
So I've drawn.
Oh, sir, I understood why the 90 degrees. Why it's a right angle.
So this angle I've made from here, okay, it's some angle. And if I were to draw from the same arc, if I were to draw to the center of the circle and make an angle there, okay, yeah, Naren, you figured it out, right? And I've just shown Anaria before we.
Yes, sir.
So Anaria, there's another angle from the same arc. Okay, I'm not changing the arc. It's the same arc. I've drawn one onto the center of the circle, right? That angle is there as well. Yes. And do you know
Yes,
what
sir.
the relationship between these two blue angles is? From the same arc, one angle goes to the circumference. We'll call that as A. Okay, we'll call that as A. And another angle goes to the center. We'll call that as B. And remember, they're from the same base or the same arc. So do you know what the relationship between A and B is? The angle at the center, that's B,
Okay, fine.
is double that of A. Okay, is
Oh,
double
sir.
that.
Oh, it's that theorem.
Yeah, of course.
Okay.
So if this was X, then this would be 2X. So if this was 50 degrees, if this happened to be 50 degrees. This would be 100 degrees. Is that fine? Did you get
Yes, sir.
that?
Yes, sir.
Now, if this were the arc, if if this were so for the diameter, the half the circle is the arc, right? Semicircle. So if this were the arc from the same logic, I'll be drawing one angle to the center here, right? From here, this is the angle to the center. So this angle is 180 degrees. Oops, too light. Hang on. So I'll be drawing one angle to the center, right? In much the same way that I've drawn this, I'm drawing this angle. This is 180 from the arc. I'm drawing one to the center. And from the same arc, I'll be drawing one to the circumference. So that will be half. So if this is 180, this will be 90 degrees, no matter where that is. Got it?
Yes, sir. Oh, okay.
Kind of. Naren, you've got this, right?
Yes, sir, I understood.
Okay, and let me just quickly take you through that again. I don't think you've quite got it. You're seeing all these random lines on the this thing. Bear with
No,
us.
sir. I got it.
Got it?
Yes, sir.
Okay. Okay, so just remember this is called the angle in a semicircle is a right angle. So if you ever have to give an explanation, that's what the explanation is. Okay. Okay. So this is the one that we talked about. Angle subtended at the center is twice that subtended at the circumference from the same arc. Okay. So the arc here in question is what you need to look at and memorize. That's where a lot of children get it wrong. This is the arc. Okay. Basically, the arc is the base of those two lines. I mean, where those lines meet, right? That's where the arc happens. So one angle from the arc subtends onto the center, and one subtends to the circumference. Remember, it has to touch the circumference and it has to touch the center. Otherwise, this theorem doesn't work. Okay, many times just to confuse you, the board would do strange things. What it would do is it would give you, this is this and this would be the center. And just to tempt you, because you kind of, it'll draw an angle here and it'll draw an angle somewhere here. It won't touch. But you look at the pattern and you think, hey, this might actually have a relationship. There's no relationship. Whatever these angles are, even if they do have a relationship, we have no idea what they are unless they touch the center and they touch the circumference. Okay, got it? Just watch for that.
Okay, sir.
So the board can be a little bit tricky, and there are a lot of times these kind of questions appear. There'll be some other relationship which is due to some other reason, but it won't be this reason for sure. So this is a theorem that's pretty straightforward. Just from here, the takeaway from this, or a way to remember this, is just remember that these two lines always meet at the same point, and you can draw either an arc from it or you can even draw a chord from there. Okay, so they'll share the same chord or they'll share the same arc. Their base will be either the same arc or the same chord. Okay, just remember, and one is to the center and the other one is to the circumference. Anyway, we'll just do a few problems based on that as well. Okay. Now, this is a continuation of the previous one. This might look a little complicated, but trust me, this is exactly the same as the previous one, except for one small difference. So this is again sharing the same arc, right, guys? Or the same, if you see these two angles, the triangles that are made from them are sharing the same. So I'm going to draw, okay, hang on. Let me redraw this in another thing. Okay. So remember we talked about, you know, in the previous theorem, okay? And trust me, this is easy. This is actually a piece of cake when you see how this works. So from a particular arc, I've drawn this angle. Yes,
Yes, sir.
Anaria, I've drawn this
Yes, sir.
arc. I've drawn an angle. So far, so good.
Yeah.
What if I draw another angle from the same arc? Would you think that that angle would be equal?
Yes, sir, because they share the same arc with when joined from the center.
This is x, then this would also be x. Anaria, if two angles are coming from the same arc, then they would be equal.
Equal.
If I were to draw another angle somewhere else, that would be equal as well. But as long as the base is the same, that arc has to be the same, and these two tips have to touch the circumference, all right? And these two. So these are the things to note in this. The base should be the same, and they should be touching the circumference. Okay. There's another one here, and there's another line here. That angle would also be x. No problem. That angle would also be x. Okay. So that's what this theorem says. Remember that visualize a sort of arc at the bottom. If you don't visualize that arc at the bottom, right, the thick line that I'm drawing, then this figure looks a little bit disorienting. But if you draw this, I think it becomes a lot clearer, at least according to me. Then you quickly imagine that, hey, there are two angles here that are coming off from the same arc. Okay, always look for the base of these two angles, and are they on the same arc? Okay, is that fine?
Yes, sir.
You want me to this thing it? You want to take a screenshot or anything? Oh, this is okay.
Okay.
Okay, so angles subtended from the same arc are equal. Okay, now we come to something called a cyclic quadrilateral. So first and foremost, before we actually go to this theorem, what's a cyclic quadrilateral? What would you call a cyclic quadrilateral?
So when all 4 points touch the circumference of the circle.
You're okay with that?
Yes,
Yes,
sir.
sir.
So cyclic quadrilateral is one where all the four, the angles need not be 90 degrees. They could, but they could be something else as well. And the opposite angles are supplementary. Okay, so that's one striking feature of a cyclic quadrilateral is these two opposite angles add up to 190. These two angles, opposite angles, they add up to 190. They are supplementary. They are supplementary. The same with the other two angles on the other two sides. These two angles also add up to 180. That okay, right? Also, I wanted to show you this appears again many times. If I were to extend this line here, and I were to ask you the value of this angle, okay, and which angle would this be equal to? Um,
It, so it would be equal to the opposite
this
angle.
is x, and this is 180 minus x. So what would be the value of this angle?
So
Anyone?
it would be x.
Anaria, are you okay with that? The fact
Yes,
that
sir.
it x. Okay, just yeah. So if this is 70 degrees, this would be 110. Okay, and why would this be 70 also? Because 180 and 70, they lie on the same straight line. Yeah. Okay. But this is not that important a theorem because you can quickly work this out. But the fact that the cyclic quadrilaterals, the opposite, whoops, what's happening here? There's a mistake on this. This was 180 minus x, not x. This is 180 minus x. Okay. This is x. This would be 180 minus x. You want to take a screenshot or something? Okay, so these two angles are supplementary, all right? Fine with this, can we move on?
Yes, sir.
Yes, okay. So lots of theorems so far, but you've got a grip on this, right?
Yes, sir.
Want to, do you think we should do a few problems? We have some. So I'm gonna take on a few problems from your book, and let me know if there's anything in particular that you want me to do. Do you guys have your textbooks?
Yes, sir.
Yes, sir.
Okay. Do you want to look up a problem and tell me a problem from your book? I can look that up.
1 second, sir.
There is any problem? Any particular one that you want me to solve? Or I think Andrea is looking for a problem, but
Yes, sir. I'm also looking.
the very first problem a lot of students find tricky. Do you know that? The very first problem in 17A. Just see if you're okay with that before we move on to the other problems, okay? See if you're fine with it.
Yes, sir. The first one is okay.
Should I pick one?
Sir, can we do the 33rd one?
Or in the A exercise?
17A, sir.
Okay. 33rd is the figure shows two circles which intersect at A and B. Is that the one?
Yes, sir. That one.
Hang on, let me just take a quick screenshot from this.
Sir, we don't have the 33rd one in our syllabus.
You don't?
Yeah, we don't.
Oh, okay. Okay, in general, I thought it's only the ones that involve proofs, but even this one isn't there, is it? This one's looking for measurements, but you don't have it. Okay.
No,
Naren,
sir.
I think that's been taken away from the syllabus. You're sure
Okay,
about
sir.
that, right?
Yes, sir.
Else? Guys are okay with the 36th one?
Yes, sir, we could do the 36th one.
Just paste this.
Sir, could we do the 36th one?
36th we can do. Okay. Just give me a second. I'll just paste this onto the. Just a moment. Let me just. I'll share the screen with you in a moment. This one, right? You can see it on the screen.
Yes, sir, it's visible.
Yes, sir.
ABCD is a cyclic quadrilateral in which AB is parallel to DC and AB is the diameter of the circle. So that's given to us, and that's a very important fact. Okay. AB is a diameter of the circle. That means this is the center. Given BED, angle BED is 65 degrees, calculate DAB. So this angle is given to you, 65, and calculate DAB. So we don't know this angle. And BDC, this angle. Okay, so just so you know that ABCD is a cyclic quadrilateral and AB is parallel to DC. Okay. All right. So anyone want to have a go at what's the first impression that you get from this? Anybody? Naren?
So we have a 90-degree as in the semicircle,
Which angle is 90
ADB,
degrees?
ADB.
ADB. That's absolutely right because AB is the diameter, and from the diameter AB, you can draw triangles such that vertex D touches the circumference. And we just studied that angle in a semicircle is 90. So this angle, this whole angle will be 90. And this is the triangle in question. This is the triangle in question. So I'm going to isolate that, right? So Naren, that's absolutely right. Anarea, did you follow what how
Yes, sir.
this was
Yes, sir.
90
Yes,
ADB?
yes.
Okay, so I'm going to write that angle ADB is equal to 90 degrees, okay? Because AB is the diameter. And you've got a right angle in a semicircle is this, okay? I'm not going to take time writing that, but I'm letting you know that you have to write the reason in the exam. Otherwise, they could pull you up for that. Okay, so that's the first piece of information. Fantastic. That's 90 degrees. Okay, what else? What else do we know?
So would DAB be 65?
Brilliant, brilliant. Okay, and Naren, did you figure that out as well?
Yes, sir.
Yeah,
Angle in the same place.
excellent, excellent. Well done, guys. Yeah, so because this is the arc, do you visualize the arc here? Andrea, is that what you did?
Yes, sir.
And then from that arc, you have two angles that are the same. Yes. So we've got the answer to one of our questions. DAB is 65 degrees. Brilliant. Okay. So now what's the next piece of information? Anybody?
So would could we find out angle DBA, and then after that, since it's an interior opposite, would BDC be that?
Correct, that's right. But the reasoning is not interior opposite, it's alternate.
Oh,
Alternate.
yes, sorry.
Yes, it would be. And Naren, how would you find angle
Uh,
DBA?
it would be 180 minus 90 plus 65.
Correct. The green triangle, we know two of the angles already. You're right. And it's easy to find out the third because all three of them have got to add
25.
up to 180, right? So 90, 65, and I think the remaining would be 25.
25 degrees.
So which would, according to the reason that Andre gave us, this is 25. Well done, guys, both of you. Good job. It was fairly simple, right? If you look at it
Yes,
this
sir.
way. You want to make a note, you can make a note, and meanwhile, we can even consider doing another one.
Sir, can we do 44? 17A 44.
Yes, sir. Can we do 44?
44 looks deadly because of the tone of voice in
Yes, sir.
both of you saying it is like, can we do 44? Okay, I just exaggerated that, but yeah, okay, let's have a look and see. I'm going to paste that. Okay, just give me a few seconds. All right, copy. So I can go past this, right? You've written everything in the previous one.
Yes, sir.
Yes, sir.
So I'm going to just try and enlarge this diagram. Though I can see this, but I think we would still need to enlarge if we need to write something in that, mark angles or something. Okay, question 44. In the given figure, AC is the diameter of the circle. Okay, so the moment they say diameter of a circle, what strikes you? I've not even read anything further, guys. The moment we say diameter of a circle, anything strikes you? AC is the diameter of the circle. Here, nothing really, right? Because nothing's connected
No, sir.
to
Yeah.
making it 90 degrees. Yeah? But that's the first thought that should strike you. Hey, there might be a 90-degree angle somewhere. In this case, it's not. Okay, so AC is the diameter of the circle with center O. CD
Sir.
and CD and
Sir.
BE are parallel. CD and BE are parallel. CD, that's this, and BE are parallel. Okay.
The angle BEC is easy to find.
Angle DEC is equal to, say that again.
So, angle AOB,
Given
angle
as
A,
80.
yeah,
Okay.
and angle ACB will be 40 because it's of the same segment.
So these are parallel. Let's have a look. These two are parallel. The arrows indicate that they are parallel. Okay. Yeah, you said the angle
ACB is 40.
AOB is 80. Okay. So this is the arc in question, is what you're saying?
Yes,
Yeah.
sir.
And this is the angle that comes off that arc, right? Let me just draw this in another color. So this is the angle, that's the orange lines are making the angle that comes off from that arc. Yeah. And Yes, you're absolutely right. I'm going to draw the other angle that you're talking about. So this angle you said is 40, right?
Yes, sir.
So Naren, absolutely right. And Andrea, did you
So
work
I
out?
didn't understand that.
Let me just draw this in isolation. Just that bit. Oops. Just that bit here. So I've only drawn that part of the this thing. Okay, I've only drawn that part. This angle is given to you as 80. And if you look at this, this comes from that same, both of them have the same base, right? They have the same, they are from the same arc, right? So this would be
Oh, okay, okay. Okay,
half
sir,
the
got
length.
it now.
So that's what you got to spot for. So I think what Naren looked for was that this arc here was the same, right? They shared the common arc. One
Yes, sir.
angle went to the center, the other angle went to the circumference. Is that what you did? Is that
Yes,
how
sir.
you figured it out? Excellent. So that's 40 degrees. Brilliant. ACB is 40. Fine. Now, now what is angle BEC? See if you can work that out. Anybody? Okay. Before that, what's the next piece of information that you can get? Okay,
Angle
ACE is given
BOC.
as 10. Okay, ACE is given as 10. This little angle that I am highlighting in orange, this little angle is 10 degrees. Okay,
Angle BCA is 50.
BCE is 50. Yeah, okay, that's right. Absolutely. So that's just 10 and 40, right?
Yes, sir.
So, Canaria, I don't know if you understood what Naren
No,
said, but
sir, I got that. I got that.
got that, right? This is 10 degrees, which means that this entire angle is 50, right? This whole thing is 50
Yes.
because one of them is 40, the other is 10. Okay, that's fine. That's one more piece of information that we've got. Anything else?
Angle BOC is 100 because AOC is the diameter and AOB is 80. BOC.
Um, AOB is 80, correct? AC is the diameter, right? So I'm just
Oh,
going to erase a lot of stuff from here because I think it's getting in the way now. Yeah, correct. So this is 100. You agree with that? And this is 40, of course.
So the
Guys,
angle BEC would be 50.
no, BCE would be 50 because this little bit is
No,
10.
no, sir, because BO and CO
Yeah,
touch the
yeah,
point, and then
yeah.
E is at
That's
the.
that is right. That is right. Naren, you got this as well. Why this is 50?
no, sir. Could you
Yeah, I
repeat it?
will. I will. So I think Andrea spotted this arc here, and because of that, there's an angle that's going to the center, which is 100, and
Oh,
then
yes,
one
sir.
going to the
Yes, sir. Understood.
circumference, and that's 50. Sometimes in the clutter, it's a little difficult to spot, but well done. Yeah. So that's 50 degrees. Okay. Well done. Good job. Okay. So what else? Any other piece of information? Yeah. So BEC is one that we worked out as 50 degrees.
Angle ECD would also be 50 degrees.
Angle ECD
D would also be 50.
Yes, sir.
ECD is what you said.
Yes, sir.
Okay, good. ECD is 50 degrees. Okay. And why is that?
Alternate interior angles.
That's 50 as well. Can someone tell me what this angle might be? This angle that I'm just shading in blue
So
right now.
40 degrees.
Yes, sir.
40 is what? Radian. It's an isosceles.
PCD 100.
Lots of angles that we've figured out.
So angle BCD will be 100 degrees as
Yeah.
uh,
BCD is 100. Did you get that as well? I think that's just addition, right?
yes, sir.
So BCD, the red angle. Okay. This red angle is 100. You realize how it's 100, Andrea?
Yes, sir.
This is 50, this is 40, and this little is 10. So add up all the three, you get 100. Good job. Well done, Naren. 100. Okay, angle CED. CED is the remaining one. How do we figure that out?
Angle DEB is equal to 80 degrees.
So opposite angle supplementary.
DEB is 80 degrees, so DEC should be 30 degrees.
And why is it 80 degrees?
Opposite angles of a cyclic quadrilateral are supplementary.
Did you get that, Andrea?
Yes, sir. Yes, sir.
30. So this is 30. CED, they've called it. That's 30 degrees. Yeah, so this sum involved a lot of the skills that you needed, or a lot of the theorems also. Some basic skills, parallel lines and interior angles, transversal. Then you had a couple of the theorems. Then you had the fact that the two radii in a circle are equal, so the isosceles triangle. So little things like that. So a lot of skills, but I think you spotted those arcs well. I think this time that was fantastic. Good job. Okay. So I think we are nearly done. We're pretty much done for today. Can we close up now?
Yes,
Okay,
sir.
sir.
Yeah. So try and come in at use the same link and try and come in at 8:30 so we can get a full class.
Yes, sir.
Sir,
To,
I did, sir, but then it mentioned that the host was in another meeting.
okay, okay, my bad. You have my numbers, right? So you can ping me as well if anything like that happens.
Okay,
I
sir.
think
Yes, sir.
Naren did that in the morning. Sometimes I don't know what, there must have been some issue with Zoom. So let me check on that. All right.
Yes,
And
sir.
practice as much as you can. Whatever we learn, just practice. So I'll see you guys tomorrow. And
Okay, sir.
okay, have a great day. See you guys. Bye
You
bye.
too, sir. Thank you,
Thank you,
sir.
sir. Same to
Thank
you.
you. Yeah. Bye.